Chapter 36, Geometric Optics. Now that we have the Snell's law of reflection and refraction, we are able to apply these laws to study various cases of image formation. And this is the subject of this chapter, Geometric Optics, in which we study how an optical instrument can form an image. And again, the laws that we're going to use would be the Snell's law. There are two cases, of course, for the Snell's law, reflection and refraction. When an image is formed by reflection, the instrument involved is called a mirror. As you know, we can either have a plane mirror or a curved mirror. We'll study both cases. And if the image is formed by refraction, then the instrument in question is called a lens. I'm sure you have seen both cases. Now we're going to study them systematically. Now let's review the idea of an image, an optical image in general. We here have an object, okay? And light rays, you can imagine light rays coming out of this object. These light rays will be passing through or getting reflected by a set of optical instrument. This can be a mirror, can be a lens, can be the combination of both, and so on. And whatever happens, after the light rays get processed by an optical instrument, they come this way. Okay, they merge at that point, and that point would be the image formed by this object due to the optical instrument in question. Again, if the optical instrument is of a mirror type, then it forms an image by reflection, and if it's of a lens type, it forms an image by refraction. Now, when it comes to optical images, there are two types of optical images that we have to distinguish. One is called a real image, and the second type is called a virtual image. Okay, here's the case of a real image. I have light rays coming in, okay? They actually converge at that point before reaching our eyes. This is a real image because actual light rays pass through that point, and that point would be illuminated if I put a screen here. Okay, if I put an actual screen here, there will be a bright dot on that screen, meaning light actually pass through that point. Okay, this is the case of a real image. What is a virtual image? Well, here's an example of a virtual image. I have a beam of parallel light, which do not really converge to any point, but then I put a piece of instrument here, optical instrument. I'll show you examples how to do that. And what that piece of instrument does is that it causes the light rays to go sideways like this. Okay, it causes those go sideways like this. And we look at these light rays. This is our eye. We look at these light rays, and what do we see? Well, we see these light rays coming towards our eyes, and they appear to be originated from there. Now, is there really something there? Not really. The light rays are like this. Okay? Nothing is really there. This is not where light rays actually originate, but it just appears to be so. In fact, look at these two cases. Look at these two cases. Here we have light rays going this way, coming from a real point. Here you get light rays which appear to be divergent in the same case as that, except that they do not really come from that point, but they appear to be doing so. This is an example of what's called a virtual image. Okay, no light rays actually pass through that point, but it can nonetheless still be very convincing. The most famous example of a virtual image would be that formed by a plane mirror. You know, when you look at a mirror, you see yourself. That image is definitely virtual because that image is formed behind the mirror, and of course behind the mirror there is no light. It's dark, right? So obviously no light can pass behind the mirror. The image formed is a virtual image. We'll see. We're going to study both real and virtual images formed by both mirrors and lenses. Okay, as our first case, we're going to study image formation by reflection. In other words, mirrors. Okay. Now, speaking of mirrors, the simplest of all mirrors geometrically will be a flat mirror or plane mirror. It's just a flat surface. Right? I have here an object, and that object, of course, emits light rays. Okay, it emits light rays. I can draw these light rays in all directions. What I want to know is what kind of image is formed by this plane mirror. Okay, now instead of drawing the behavior of all these light rays, we only need to draw two such light rays. Because if these two light rays, after getting reflected by the mirror, if they converge at some point, then in order to form a clear image, all these other light rays, after getting reflected, must converge at the same point. Okay, this is how you form a clear image. And let's see how we might choose two representative light rays. Okay, now one ray is very clear. I simply aim straight at the mirror, 90 degrees. You know how that ray is gonna get reflected, right? Simply goes right back. Okay, it goes right back. That's one. Now let's look at another one. Another one, say a light ray like this. Okay, what is this light ray gonna do? Well, it's gonna be reflected like this. Okay, like this. And these two angles, theta and theta, must be the same. That is the Snell's law of reflection. Okay, now suppose I look at the mirror. This is me looking at the mirror. What do I see? I see one light ray going this way towards my eye, another light ray going that way towards my eye. Okay, even though there is really no light behind the mirror, these two light rays appear to originate from that common point. Okay, as a matter of fact, if you draw a third light ray, you're just going to get the same thing. A third light ray, for example, coming this way, and it's going to get reflected this way, and if you extend it backwards, they appear to be from the same point. Okay, this is due to the simple geometry setup. So you have, after getting reflected, you have a whole bunch of light rays coming this way, coming this way, coming this way. They all appear to originate from the very same point, somewhere behind the mirror. Is this the location of an image? Yes, it is, by definition. Okay, is it real or is it virtual? Well, no light rays actually pass through this point, right? It's dark behind the mirror, and therefore it is a virtual image. Okay, so we have a virtual image here. That's the image. And where is exactly that image? Well, take a look. You look at, say, this right angle triangle and that one. Okay, they share one common side. Right? They share one common side, and also, you know, this angle equals that angle. That is because this is a straight line. Okay, this is a straight line, right? And on the other hand, this angle equals that angle because these two lines are parallel. They're both normal lines. And what does that tell you? It tells you that these two angles are the same. Okay, so I have this pair of right angle triangle that are congruent, right? And what does that tell you? It tells you that this distance equals that distance. So this is how you find the image formed by a plane mirror. All you do is you start from an object, right? You draw a line perpendicularly towards the mirror, and you extend behind the mirror the same distance as the distance between the object and the mirror itself. This, of course, as you know, is the so-called mirror image of that object. Okay, now suppose an object has a certain orientation. The object is like this. Okay, suppose it's got an arrow. Where would be the whole image of this arrow? Well, this arrow, look at 2 points. Here's a head, here's a tail. Okay, the tail, of course, is somewhere here, right? And then I can draw these, you know, connect these 2 points. I will get the image of this whole arrow. It will look like this. I use broken lines to indicate that this is a virtual image, not a real image. Okay, you see, you have an arrow here, you get an arrow there, and it's got the same shape, same size, all right? And this is why the plane mirror gives you a faithful representation of the shape and size of the object. That is why when you look into a plane mirror, you see yourself the same as the real person. Okay, it's a faithful representation. It does not distort the image, doesn't make it bigger or smaller, doesn't make it wider or narrow, whatever. So this is what a plane mirror does, as it's supposed to. But it's important to know that a plane mirror produces a virtual image, okay, of the same shape and size. And it's the right side up, by the way. It's not upside down. Okay, it's the right side up. That's, of course, an important feature of the image formed by a plane mirror as well. Okay, now let's extend our discussion about plane mirrors just a little bit. One extension is the so-called multiple reflections. So I have more than one plane mirror at work. In this case, I get M1 and M2. They are perpendicular to each other. So there's really a corner, a reflective corner. And then I have an object here, I want to know how many images are formed by these two mirrors of this object. Okay, now first of all, this mirror M1 can produce an image here like this, right? We call it M1 prime, and it can also, okay, by the way, these two distances are the same. It can also form another image. Actually, the second mirror M2 can also form another image of the same object there. We call it M2 prime. Okay, and then both of these are through single reflections, and that is, you only reflect off of one mirror. Is it possible for a light beam to be reflected by both of these mirrors, M1 and M2, to form an image? Well, of course, it is possible. For example, suppose I have a beam of light coming from the object like this. So it hits the first mirror first. Okay, where is it going to go after getting reflected by the mirror? Well, simple geometry tells us it's going to go this way. Okay, it's going to go this way. So now it will enter the surface of the second mirror, so it's getting reflected again. All right, it gets reflected again, and this time it's going to go that way. All right. So my question is, where is the final image? Okay, where's the final image? You know, it's certainly gonna go that way. And in order to find the final image, let's take a look. Okay, a single light ray is not going to be enough. I need to draw another light ray getting reflected by both of these mirrors in order to know what the image is produced by these two mirrors simultaneously. Okay, so let's draw another line. This time I'm going to draw something like this. I'm going to draw a beam like this. This beam will get reflected to somewhere here, right? Which is again reflected like that. Make sure these don't go the same. Now, suppose you look at these two beams, one this way, one that way. They appear to be from where? They appear to be originated from here, right? Okay, now if you do all the drawing correctly, what you would notice is that this third image really is the mirror image of M1 prime reflected by M2. So and that makes sense, because this M1 prime is after one reflection, and you're reflected by the second mirror M2, then you get the third image. Okay, let's call it M3 prime. And this is an image getting reflected by M1 first and then by M2. You can also form the image produced by M2 first and then M1. So so you can start from M2 and reflect it by M1, you get yet another image. So in principle, you can get a total of 4 images: M1 prime, M2 prime, and then 2 more due to both double reflections. Okay, so this is an example of multiple reflection. And the number of images in general would depend on the angle, okay, between these two mirrors. Suppose I have a mirror like this, M1, and a second mirror, M2. It depends on this angle. In general, the smaller this angle is, the more images you can have. Okay? In fact, if this angle is 180 degrees, that means these two mirrors really just one mirror. You can only have a single image. And yet, when this angle is very small, in particular, when these two mirrors are parallel to each other, you get two mirrors like this. So the angle between them really is just how many degrees? Okay, if you extend it all the way to infinity, the angle between them is what? It's 0 degrees, right? It's 0 degrees. So you got two parallel mirrors. How many images can you possibly form by these two mirrors? Well, in principle, infinite numbers. All right, you have an object here, right? So here's one image, right? That's one reflection, and here's another image, one reflection, and then this guy can reflect it by that one, and that one will again be reflected by this one. It can go back and forth. In principle, infinite number of images. You probably have noticed that actually. Have you ever wondered if you remember when you sit on the chair of a hair salon? Okay, and the hair salons typically have mirrors on both parallel walls. So you look at the mirror in front of you. You probably would notice that inside the mirror you don't just see yourself. You also see another mirror, which hangs on the opposite wall. And inside that mirror, you can see another image of yourself. Okay? And in fact, this can go on and on and on. Of course, the image will become really, really small. You cannot see it. But in principle, you can see an infinite number of images in that case. Okay, so that's how we deal with multiple reflections. Now, another application would be the so-called diffuser. What we have here is a surface that is not quite 100% flat. Okay, it is made of irregularly oriented surfaces, irregularly oriented plane mirrors. What's the application of a diffuser? Well, the thing about a diffuser is that light coming from, say you got a beam like this, okay, coming in like this, right? It's not going to get reflected right back. Rather, it depends on where you strike it. See, this particular beam will get reflected this way. That one's going to get reflected this way. And then that one is going to get reflected this way. And that one is going to get reflected this way, and so on. So every beam will get reflected in different directions. Okay? It is therefore impossible to form a well-focused image if the surfaces are randomly oriented. That is what's called a diffuser. Sometimes we don't want to have just a flat mirror that forms a clear image. Rather, we want an incoming beam of light to reflect in random directions, so as to diffuse the light. Okay, so what you see is, the effect is just a white screen. Okay, illuminated white screen instead of a polished mirror. This is sometimes a desirable effect. That's how a diffuser works. In fact, if you look at the light panels on the ceiling of our classroom, these are diffusers. Okay, so it's not a flat surface. Rather, it's made of surface of random orientations. All right, one more example of mirror reflection. How does water, a large body of water, reflect an image? Suppose here, this is the sun, okay, and this is the ocean. Now, you probably have noticed that in the case of the ocean, you don't really get a clear, at least most of the time, you don't get a clear image of the sun. Rather, you get something like this. Okay, it seems that the image in the water has been stretched that way. This is called tapering. Okay, it's called tapering. And the question is, how does that work? Well, you got to understand that the ocean is not a perfectly flat mirror. If it were, then all you would see would be just one clear image of the sun right here. You wouldn't see tapering. So where does the tapering effect come from? Well, in reality, the ocean surface has ripples, right? It's got ripples like this. So you can think of a whole bunch of ripples like this. Okay? Now, in each, here is one ripple. Here's one such ripple. Okay? And when light comes in, because here is a curved surface, it's going to get reflected in all kinds of directions. All kinds of directions. Okay? So, even though if it's a flat mirror, you wouldn't see anything except here. If you think of these as a whole bunch of ripples or ridges like this, every one of these ridges, when light from the sun casts on these ridges, it's going to reflect in all kinds of directions, including one particular direction that's aimed at our eye. For example, if your eye is here, you're going to see this. You're not going to see those light, but you're going to see this. Okay, that is why over a very long distance, you are going to see reflections. It's because of these ripples or ridges. That is why you have the so-called tapering. If the water surface is really, really calm, okay, such as, let's say a small pond or small lake with very little wind, then it is actually possible to form a really nice isolated image of the sun or the moon. But in the ocean, in the case of the ocean, it's not quite possible because there's always enough wave on the surface of the ocean. So you're going to see this so-called tapering effect. Okay, so you see a lot of the everyday phenomena will start to make sense if you look at the physical principle behind it.